get started. So today is the last day in the similarity section on class, where we're talking about kind of similarities and distances and how do you use them efficiently. And then starting on next week, Monday, we'll start talking about clustering. And so if you weren't convinced that it was really important to think about the intricacies of these distances and similarities, we'll start to see why they're important in the section on clustering. Right? And hopefully this persists the rest of the semester as we see more and more kind of different and more complex types of analysis. And we'll see that, this choice of distance and similarity and what you can do with it is kind of affects what you can do, and also kind of the modeling that comes out of everything that you end up doing. You also turn in your proposals for your projects before class. So I'll start with TA to sift through these, and if there are any issues with them, we'll try and get feedback. At this stage, most of the groups will not be getting kind of direct feedback on the proposals. If everything is okay, I'll say it's okay. If you want feedback, the best way now is to kind of come talk to me before, after class, or in the office hours. I will try and do something, I think right after spring break. I think that's when I'll try and do it, where I'll try and schedule like 5 minutes with each group to give actual feedback at that point. At that point, hopefully you've done more, and I'll give more pointed feedback. But please come and ask me during office hours before, after class for additional feedback. And I'm always happy to do that. And I usually try and stay as long as needed after class to answer questions about stuff. Okay, so the plan for today is to talk about, I'm going to give a couple more examples of how you take data, from some form of data, which is more complex, and you map it into RD. Right, so I'm going to somehow take some data, and we're going to talk about two things. We're going to talk about words, and we're going to talk about and we're going to talk about pictures. And so the way we did words are going to be different than what we talked about, where we took whole text documents. Now we're just going to talk about individual words, and we'll see that this is a little different. Then we'll talk about this approximate nearest neighbors. Okay, so locality sensitive hashing was essentially allowing you to have a big data set and ask which other data points are nearby in the data set quickly. But there's kind of a slew of other techniques for doing this, and we'll kind of walk through these and what these work. And sometimes these are competitive with LSH, but they're mainly for Euclidean distance. Okay, there's some extensions to other distances, but they're mainly designed for data that's in RD. But as we'll see, as we saw before, and we'll see again today, there are a lot of instances where you map data into high-dimensional vectors. So it's a high-dimensional Euclidean vector, and these are the appropriate things to do. So just give you the sense that this isn't it. And then we'll talk about we'll do this 20-minute things about some ethics of data representation at the end of class. So I'll try and get as far as I can through the material in the notes. I kind of move stuff around a little bit this year, so I may not cover quite everything, but we'll stop at 4 and do this discussion aspect. Okay, so I want to give some examples now about getting high-dimensional data. And the first thing I want to talk about is this fairly kind of new idea called these word vector embeddings. And so I think this was first proposed starting in like 2013. So it's not very old. but it's really changed a lot of ways how people process data, and we'll see that it kind of magically gives this representation, which allows you to immediately kind of ask a bunch of questions about the representation of words that were much more complicated than before. That's because we're basically taking words and embedding them into RD, right? So the idea here is we're going to start with some large piece of text, right? And think of this as like all of like all of Wikipedia, okay? And so what I want to do is I want to understand the like individual words in the English language, right? So if there's some, this is going to be some long string of text, and maybe I ate an apple. It was good, right? There's some piece of text like this, and I want to understand something about the word apple. What I'm going to do is I'm going to look every time the word apple occurs in this whole corpus of text, and I'm going to look at some neighborhood around it, and I'm going to see which other words appear in this neighborhood around it, right? So this idea of 3 words on either side is kind of not abnormal. This would be the continuous bag of words model, or CBOB, as this is called. Okay, so for apple, I'm going to now think of initially store some vector. I'll call this B apple, which is going to be a long vector. And so let's say that I'll just condense this. I'll say there's some index I, which represents apple, and I'm going to have these I1, BI2, up to BIJ, up to BIN. There's a total of n words in this kind of that I'm keeping track of. So I may not keep track of every single word I see. Words that appear once I might ignore. Let's say there are like 1,000,000 words I keep track of in this vector. So these are going to start out being super, super big, right? And so if I look at the word and let's say that J is the index of an, then every time I see this, I'm going to increment this value. So Bij plus plus, because I saw the word and, right? And so for each of these words in this kind of window, I'm going to increment this vector here. Okay, and so this is based on this corpus of text, I get some big vector representing the word apple. Okay, and this isn't quite exactly what you do. I'll kind of, this is not going to be the final representation of this. Okay, so usually I start by creating some word counts around each word, and then I somehow want to use this to create some sort of embedding. Right, so what's going to happen is I'm going to create, think of this high-dimensional Euclidean space, right? So there's some origin here, and so I'm going to get some vector that represents the word apple. I'm going to get another vector that's going to be representing the word pear. Okay, and so apple and pear, they're both fruits. Turns out they're likely going to be close to each other in this space if I do this correctly. I could have just as easily said I ate a pear and it was good. This would still make context. I might see a similar thing of text. It may be a instead of an, I guess, right? But it's the rest of the words are the same. Right, so if you have a really big piece of text, you'd probably get apple and pear have similar context to each other. Right, so they're going to appear similarly in this space. Okay, And what's going to happen is there's going to be some region in the space where you're going to have like all of the fruit in the space, and there's some larger region here that has like all of the nouns, right? And then a different area with the verbs and so forth, right? And so typically you embed this into a 300-dimensional space. Typically, you know, it could be 1,000, could be 200, but typically you map it into a 300-dimensional space. And so this is useful for things like, so things you can do with this, you can find, so synonyms for words, but just by looking at a word and finding the words nearby, there are these corpuses of synonyms of words, and if you look at where the embedding, they're tended to be embedded so near their synonyms to each other. Okay? Yep.
So what does the 300 means? Does it means number of words?
No, it means the number of dimensions in the representative vector, right? So this vector VA is going to be V1, V2, up to, or VI1, VI2, up to VI300. Okay, so over here, I create this B vector, which is 1,000,000 dimensions. This is a big pain to work with, right? I may do this internally to initially keep track of stuff, but I want to give this to some data analysts to do clustering or something on, and for that I'm going to work with a 300-dimensional space. I'll mention in a second how I go from 1,000,000 to 300. So there are multiple ways, so I'll mention one of them. Okay, but let me kind of give a context of what it is we're trying to achieve here first. Yeah.
So the dimensions, they represent the context modes, I mean, and the frequencies that you're maintaining. The 300 dimensions over here. I mean, what is each of these dimensions?
Yeah, so it's basically just some feature value that gives a 300-dimensional representation of the word. Okay, and how they get to that is kind of a black box. Okay, I'll explain one way how to do it, and you'll see that way. But the other way is like take this and they throw it into like a neural net, and they take some hidden layer in the neural net, and they say there are 300 elements in this layer, and those are my dimensions. I pass the word in, I run it up to this layer, I get 300 dimensions. That's my representation, and that tends to work. You have to set it up the right way and so forth, but it's kind of, they don't have explicit meanings by themselves, but their Euclidean distance tends to be useful. Okay? And one of the reasons is similar words are close to each other. There are other sorts of things you can do with this. One is this idea of analogies. Okay, and this is one of the reasons it got kind of popular, in that you could take vectors of 3 words. You could do something like V king minus V queen plus V man. Okay, so I get representations of the word king, of queen, of man. I subtract these two, and this gives me kind of a vector, the king to queen vector, and I add this to man, and this is often close to V, so V woman. Okay, so you could think of, if you took like one of these standardized tests, you would get questions like this on the test. King and queen is to man and blank, and you have to say woman, and it can kind of solve these fairly well in some contexts, right? So I can take these vectors and I can say, okay, apple is to pear, right? Apple is to pear as like, you know, and maybe I add this onto this other vector, cow, and I add this vector here, and maybe the closest word over and here, there's some, I end up at this location, and somewhere nearby is the sheep. Okay, maybe, you know, apple is to cow, apple is to pears, cow is to sheep, possibly, I don't know, right? Maybe you can discover new things, but they found there are these big data sets of analogies, and they tested them, and they did better than you would probably expect before you would have thought doing this. Right? So they capture some other information, some linear structure somehow when you do this embed. Okay, and then one final thing I'll mention that it does, that you can kind of get out of this, is you can find these directions that encode certain concepts. Okay, so one of these might be something like, like sentiment. Okay, so I want to think, do I like this or I don't like this? So there's a common issue in understanding language. Like, let's say there's a tweet that is about some company, and I'm working at some financial firm, and I want to look and see, are these tweets negative about the company or positive, and use this as an indicator of, should I be worried about the stock if this changes? Right? And so sentiment analysis is this a positive tweet about the company or a negative tweet? And one way to do that is to look at all the words in the tweet, and if they're mainly positive or neutral, then I think it's positive. If they're mainly negative, I think it's negative. And this idea of like the sentiment. And so there could be these ideas like there is a certain, some vector where this direction is good and the opposite direction is bad. So the values, so if I have a vector that's up here, right, it's more on the good side, and something down here might be more on the bad side. If I can identify some dimension in the space, I can project things onto this dimension, and I can score how good or bad it is in terms of the sentiment of that. Right? So if someone write happy, so V happy might be a good sentiment, and like angry. If I wrote I'm angry about Sears or something, right? It's a bad sentiment. So maybe this is V angry, right? It might carry some connotation to it. Okay, and so I want to do that, and I might be able to learn that by taking these 300-dimensional representations and labeling some words that I know are happy and are positive or are negative sentiment, and then building a classifier, just a linear classifier, and that'll be defined by just some vector in the space. Okay, and this works okay, right? This is one way to build these sort of classifiers of words in the space, and helps people identify certain things about the language. Okay, so there's lots of cool things people have done and shown that works fairly well with this sort of representation. Okay, few questions back there.
So what about a word that can be both good and bad? Will that be a type of vector in its own, or will that be described by the vector?
Yeah, so words that have multiple meanings, like apple, right? It's a fruit, it's also a company. These words don't work as well. They could, depending on which version occurs more, it might end up getting weighted more in that context or the other, or it might fall someplace kind of in between. Maybe only if it's strongly correlated very far in one direction when you actually give it a score. Yeah, there's lots of questions like this of what's the best way to do this. But these kind of representations are new, and people are still figuring out how best to use them.
So I'm guessing sarcasm tends to throw it off as well?
Yeah, so sarcasm is a challenging thing. Ask if you talk to Ellen Ryloff about that, she's like one of the world's experts in understanding sarcasm in text. So she would probably not advocate this approach, but yes, sarcasm is difficult. Yes.
And I have another question. So can this handle like reverse relationships, like king is to queen as she is to, would it give me he?
Yeah, so it should work several things along this direction. So, this is like representing gender. This would be like a concept direction for gender would be captured by this king-queen vector.
And would it, so basically the way that works, is it like check? Does it calculate that delta and check in both directions?
Oh, it calculates, so it takes this green vector, so say from apple to pear, and it takes it from man and it moves it. It moves from man in this direction this amount, and then it looks what's the nearest point to my data set close to there.
Okay.
Right.
Would it check in the reverse direction as well? 'Cause
Well,
like,
that
checking the
would
reverse
that
relation-
would be doing something else,
Got it.
right? That would be assuming that this was like pair, I think. Maybe I may have gotten the sign wrong, but that may have been like if this was pair, I want to go the other way, I could do that as well.
Yeah.
These are things like works from like yeah. There's some examples where this works, some places where this doesn't work, and it's still not quite understood. This is a fairly new technology. Yeah.
So if a word has multiple senses, it won't be modeled correctly, right, in the context of the domain?
It might still be, right? So, you know, you could have that fruit is spanning this area, and apple is in the fruit thing, but it's intersecting with this other kind of thing of all these businesses. So it kind of falls in the middle there. It might work okay, and it sometimes does. It sometimes has trouble with these sorts of words. 300 dimensions is a lot of space to play with. Yeah. So, you know, it's again, sometimes yes, sometimes no. Right? It's not perfect. Yeah, and so you could try and add more context. You could try and create a different vector if you could identify which representation it is and do that. There are lots of different things you could try to improve upon this.
So do we only use context features to generate word arithmetics? Any other numerical features we can use?
This is typically what people use, but again, you know, there are extensions of this. There are a lot of extensions of this. Like people define versions of this for understanding graphs that we probably won't talk about later in class. But like there are lots of variants of this that have come out since 2013. Yeah.
So when you classify the things into good or bad, do you need to reduce the dimension, like from 300 to like?
Well, this basically a classifier essentially reduces it down to one dimension, the good-bad dimension for for what's that's worth. It says, and it gives everything. It projects onto a single vector and says everything is good or bad. Now, maybe the right thing to do is there's like a two-dimensional subspace that really represents what's going on here. There's does bad things but is good intentioned, and there's does bad things and is bad intentioned, and so forth. Right? There's kind of and maybe you want to do that instead. You know, there are lots of things you could do. And like, it's great. You guys have all this imagination. I've given you this idea of this representation, and you're thinking of all these cool things you can do, and that's right? When you embed things in Euclidean space, objects like this, there are lots of questions you can ask. There are lots of types of things. Does this work? Does this not work? And so the research community and industry has gone wild with this sort of stuff.
How do we get these vectors to represent these words?
Okay, good. So let me try and explain one way how to do this. Okay. Right. Okay. So let me talk about these Ppomi vectors, and this will give us a representation, and this is positive. Point-wise mutual information. Okay, is what Ppomi stands for. And this is going to give us a representation in like 1 million dimensions, right? The number of words we have. But it already tends to capture this linear structure. If I use those B vectors I showed you before, those didn't work as well for whatever reason, but these Ppomi vectors tends to work as well. And then I'll mention two ways how, briefly, how you reduce these into a 300-dimensional space. Okay. Okay. So the idea here is I'm going to start with this Bi vector, which is Bi equals Bi1. Bi2, Bij, Bin, where Bij is the number of occurrences of J in the C bow of I. Right? So the number of times 8 is within the 3-word window of Apple, right? So that was the example we had before. So I'm going to start with these, and I'm also going to have some number. Okay, we're going to say M is the total, is the total number of words in corpus. Okay, so if all of Wikipedia, I just count the number of words, not the number of distinct words, just the number of words in all of Wikipedia, that would be M. Okay, and so then I can define a probability of I equals to the 1 norm of BI, which is the total number of times Apple occurs. Actually, this is divided by the context words. Yeah, so I need one other. It's not quite right.
What is corpus?
It's the whole data set. A big data set of text is also called the corpus. Okay, Ni is the number of times the word I occurs, and then Pi equals Ni over M, and Pij equals Bij over N. Okay, and then we're almost there. Then this vector that we're going to representation for Vij is going to be max of 0 and the log of Pij divided by Pi times Pj. Okay. Okay, so this is what's called the pointwise mutual information, and it has to do with so the conditional probability of seeing the word I given seeing the word J divided by the probability of seeing the word I, and you take the log of this. This is some information sense. And then I want to, if this number is too small, it can be negative. I don't want anything negative, so I make sure it's at least 0. Okay? And so this is what's called the positive, or the PPMI vector, the positive pointwise mutual information vector. I'm going to get this vector, ultimately, I'm going to get this vector VI to represent the words, which is VI1, VI2, up to Vij, Vin. Right? So this is this million-dimensional word, and each of, right? So this goes right here for each of these. Yeah.
So is that the probability of I given J, or is it joint probability of I and J?
Well, the top is the joint probability, but then I'm normalizing it. I'm dividing by the probability of J down here, and so I can interpret this as a conditional probability. Yeah.
So N would be 300 on the order-making setting? Or?
Well, no, this is still a million-dimensional. Okay, so this is still N. Think of N equals 1. Is the total number of words in the corpus, right? So not the number of distinct words. If Apple, so M is equal to sum over I of Ni. So it's this. It's like if I just did a grep over all the different words in Wikipedia, like how many words, not just like if every token I get for a word, I count how many of those I get. That's M, right? So this one is the probability that the word I occurs. Okay. Okay. So I mean, don't worry too much about where this comes from. I just want to give you and what the meaning of it. There are variants of this which are different and work nearly as well. Okay, this is just a concrete way to explain one way to do it. It gets you a million-dimensional vector. Okay, so there are two ways to get this to a 300-dimensional vector from this setting. One involves setting up setting up a deep net and running this through. It maybe takes a little bit more context than this, but it basically takes these vectors, puts them into a deep net, tries to preserve some probability of seeing something in some neighborhood based on this, while embedding it into a 300-dimensional layer, and that's what it outputs. Another one is I take these million-dimensional vectors and I run principal component analysis on it, which we'll see later in class, and this is like the generic form of doing dimensionality reduction. And that works reasonably well as well, and there's some rationale of why that works as well. Yeah.
So is there a B vector for every unique word?
There's what?
Is there a B vector for every unique word?
For every unique word that you want to keep track of. Now, sometimes if a word only occurs once or twice in your whole data set, you may not want to embed a vector in for it for various reasons. Yeah. But for every word you want a vector representation, you create this BI vector, and then you kind of do this log probability transform, and you get this VI vector. And these VI vectors have this kind of Euclidean-like property. And then you can just, one of a couple ways, reduce it to 300 dimensions. Okay.
So do we remove stop words from consideration?
You could, but I don't know whether that's standard or not. But I would probably keep them in the list of the capital N different representations. If you have the word the that occurs right before it, it probably tells you it's a noun. That's probably a good descriptor, right? Do you want to represent the word the? Maybe. I don't know. So there's some things where people understand sentences by tracing out their paths through this word vector space, and then you want all the words that commonly occur, like the. That might be useful. Yeah.
So this would require a lot of data, right? Because you cannot work on a small data set.
Yeah, right. So I would say you want at least a million words in your data set. You can probably keep some of the other numbers smaller and still get something that kind of works. As long as capital M is, say, 1 million, it's probably okay. Yeah.
Why Vij equals the max of zero and not the minimum? Because most of the time it will be equal 0. Will this make sense? I mean Vij.
So yeah, so for the ones, if they don't occur a lot together, then this will often be negative and you'll get 0. So this will be sparse. But if they occur a lot together, then this will be, I might be missing a factor in here. I might need to put M in here someplace. I'm not totally sure. But I think this is right from what but if they occur a lot together, this should be positive. Okay. There.
Yeah, so the examples that you showed us were that of unigrams. So can this be extended to n-grams in general?
You probably could. I don't commonly see that. You just get so many more things. I think you don't get enough examples of the different n-grams typically. That's my understanding, but there might be cases where you would do that.
I'm just wondering, so like, what's the numerator of the P of ij?
P of I times P of j.
No, the numerator on the P of ij. So
P of ij, n again. You're right, that should be n.
Yes, and what's the numerator? So like,
Oh, the numerator is bij.
okay, cool.
Right, that's why I needed these vi vectors. Okay, so.
You said that we don't need to create the vector representation for the words which are infrequent, like at least 1 or 2 times. But isn't the case that those words which appear infrequently are most representative of the context? Like if I have some peculiar word that says it's a disease, then we can probably predict that this document is a medical document or something.
Well, if it's a disease that occurs enough times in your document, in your total data set, then yes, you could start to say, okay, this is one of the disease vectors because of that information. But if I only see it once, I really don't know that much about it. Yeah, but these are often modeling choices again that you've hit on these different modeling choices, and people have tried. There's conventions that people use, but that doesn't mean they're necessarily the right thing to do. So I don't. I've started playing with this technology a bit more myself, and I'm learning about what is the right thing and what is the wrong thing to do in this context. But I don't really have a big picture, so I can just kind of guess a little bit at this point. But in the literature, it's people would tend to throw out things that occur very infrequently. I'll tell you that. All right, so good. So I don't want to spend too much more on this. This is kind of some cool stuff. It's because you need really big data set sizes, it can be a little tricky to play with, but there's code out there that can do some of this. And this is not too hard to implement. It just takes a lot of space. There are some data sets of pre-embedded vectors as well that you could probably start playing. And we'll talk about ethical issues of this in 25 minutes. Okay, so we'll come back to this. Let me mention a couple other things before we get back to that part of the discussion. Okay. I want to talk about one more type of data that you would embed. So I want to embed some images, and this is also pretty common. And I'll mention three things here. So first thing is, if you think of an image, it's kind of a thing, and you can kind of see my grid up there, right? And there's some smiley face, right? And right? And there's a picture of someone, right? But if you really look into this, there are a bunch of these pixels in here, right? Right, there's pixels that represent it, and this image is really just this set of these pixels, right? So if this image is going to be 300 by 400 pixels, then I can just directly map this into a vector of size of 120,000, okay? Each pixel, I can give you a value. Let's say it's grayscale, and I give you a value. It might be 0 if it's white, and it's 1 if it's black, right? And any level of gray in between there gives a different value. Okay, and so this at least classically is not an uncommon way to do with things like faces. You can get these face data sets where the faces are nicely aligned in the image, where actually they take up 80% of some maybe square image. And you try and understand this way. Or there's a lot of these very well studied data sets of like these digits, numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, where like deep learning is famous for kind of doing really well in classifying these into which number are they based on the written thing. And I think like there are like 8 by 8 image, 8 by 8 kind of sets of pixels. So not too big vectors here. So 64-dimensional vectors, or there are ones that are larger sizes. Okay, so I can directly just represent some numbers in this way, and say this would be these vectors is just some representation. Now this is kind of limited unless the data is like nicely aligned, like a face. The eyes are in the same location for each representation of the face. Maybe I can pick out the eye color, right? Or if I have 3 color channels, then I have 3 times as many dimensions. I might be able to pick out the eye color if I do this correctly. But if things are not aligned, this doesn't work as well. Okay.
So I guess why do they represent images? I guess as vectors instead of, it seems, I don't know, maybe more intuitive to represent it by like a matrix, which would preserve the dimensions.
Good. So this is a bit old school. Okay, so this is the original way people would do this, and this is good for things like if it's really blue, I can tell it's a sky or it's an ocean, right? Things like that. But it's hard to do stuff beyond that, right? So I'm going to mention a couple of other approaches. What was popular starting in like the late 90s, most of the 2000s, up until about 10 years ago, were these things, these SIFT features. Okay, and what this would do is called scale invariant feature transform, and it would identify these kind of these regions, these kind of points in the image where there's kind of a sharp boundary. Actually, the corner of the neck is probably classically not a good one, but like the corner of the mouth or the corner of the eye would be a good one. And it builds some representation around each of these features. And each of the feature elements in here maps to a 128-dimensional vector. And each coordinate has the same kind of meaning, and it makes sense to use the Euclidean distance to say how similar are two features to each other. So you would identify all of kind of the corners of the mouth in some way. And you get, instead of one vector for each image, you would get a list of these feature vectors. And then you would compare images by saying, do they have similar sets of feature vectors? And this allows the image not to be just in the same spot. Like the head could be shifted a little bit, and it'd have the same set of feature vectors. And so this was really popular. And then these deep learning came along, and these convolutional neural nets. And the idea then is, again, it takes this two-dimensional structure into account. And kind of the basic idea of convolutional neural nets is you look at every window. It's pretty similar at the first couple layers to something pretty similar at some level to the SIFT features. And then it looks at every window of various sizes. Right, it scans the window over the whole data set, and each of these goes to some representative value in the next layer of the neural net. And then it does this a couple times, and certain of them become useful features. Right? And then a representation of an image is some kind of layer later on down in the neural net. You could embed these in high-dimensional Euclidean space and do some similar things like we talked about with the word vectors as well. That's not always how they treat these things, but that's one thing you could do with images as well, using neural nets. And this would probably be the most popular way to do this nowadays. Okay, so images are also kind of work pretty well for this sort of thing where you can convert them into these high-dimensional Euclidean spaces. So we had text documents where we talked about various ways to do that. We talked about these word embeddings and now these images. There are ways to convert them into these high-dimensional Euclidean spaces. Okay. Let's see, I had a little graphic here. Let's skip this. Okay, so now for the next 15 minutes, I want to talk about so these approximate nearest neighbors, kind of different ways other than LSH to solve this problem. Let's see. So I'm going to classify this into and it's going to depend on what the dimension is. In R1, there's going to be a set of techniques we can do. In R2 to 3 dimensions, there's another set of techniques that work well. In R, let's say 3 to 10 dimensions, there's a set of techniques. And then in R, say 10 to maybe 100 dimensions, there's a fourth set of techniques. Okay, and after that, you might get lucky with the last set of techniques, or you kind of have to rely on locality-sensitive hashing. Okay, locality-sensitive hashing does not really, it may not be the right thing to do if you're in 3 to 10 dimensions, right? This kind of will deal with the very high-dimensional regime. Otherwise, if you're dealing with Euclidean data, you can often use these other approaches. Now, locality sensitive hashing with things like documents, there's no inherent dimension here, right? So, so this is only for, so when you're using Euclidean distance, but again, this is kind of the most popular and most common distance to use between data sets. Okay, so the first one, for one-dimensional data, we actually talked about this already, right? There's a simple solution. You sort data, and you build a binary search tree on top of this. And if you want to ask something, you go down the binary search tree to find the nearest point in the sorted order, and then you can have a linked list at the bottom, and you can just walk both directions in the linked list. Right, so we've talked about this before. Okay, these other approaches are going to say, in one dimension, we have this really nice solution, this binary search tree solution. We do a little bit of pre-processing, and then we can and then we can solve this question really fast, basically as fast as doing binary search. Okay, how can we do that in higher dimensions? So it gets harder already in 2 dimensions. In 2 to 3 dimensions, you can do stuff based on the based on the Voronoi diagram. This is what's called of the data. So you're going to have some data in 2 dimensions, and you can build something like this, where each cell, if I want to ask just the nearest neighbor, and I have a query point here, if it's in the same cell as this point, so if this is P1, P2, P3, P4, right? If it's in the same cell as P1, I know P1 is the nearest neighbor, and I can define this. This is what's called the Voronoi diagram. And in 2 dimensions, the size of it is linear, and I can construct it in n log n time, roughly. I think you can technically you can do it a little faster than that, but basically n log n time, and so then I can build something like a binary search tree on top of this. I kind of divide it up into cells, and I build like 2 layers of a binary search tree. And there's ways to kind of replicate this binary search tree power in 2 dimensions, and you can sometimes get it to work in 3 dimensions as well. And this gets you guarantees, and it's guaranteed to work as well as the binary search tree. But in higher dimensions, the complexity of this, the complexity, so this is, for n data points, this is of size n to the floor of d over 2. That's the floor, I should know this, it's sorry, the ceiling of d over 2. Okay, so for n points, it's the size of just representing that data structure is n to the d over 2. So in 3 dimensions, it's, in worst case, it could be n squared size just to represent it. And in 5 dimensions, it's n cubed size just to represent it. So building a structure on top of this is not going to work so well. Okay, there's an alternative that works reasonably well here, called a KD tree. And so I'll say this works in up to 3 to 10 dimensions as well. And so this doesn't have the same kind of theoretical algorithms class sort of guarantees as is these things built on top of the Voronoi diagram, but they tend to work pretty well in practice, and they're pretty simple. So who's heard of a KD tree before? Okay, good. So a lot of you have heard of this. So where do you learn this in? Algorithms class and geometry class?
2420.
2420. Oh, cool. Okay, good. So only about 30 of you, so I'll quickly mention this KD tree. The idea is that I have a bunch of these data points. Okay, and I want to kind of do a recursive split like I did, like building a binary tree, a divide and conquer approach. And what I do is I pick like the median point in the x direction, and I split this way. And then on each half, I independently pick the median point, and I split in each of these directions. And I'm kind of getting a tree, right? The top of the tree splits here, then each of the subtrees split here and here, and I recursively do this. And I choose a new dimension to split on every layer down the tree. Okay? So this is a little bit, so then I can do a nearest neighbor query, I follow the tree down, and then I have to be a little bit more careful, kind of, I can't just restrict myself to that cell, I have to look at neighboring cells as well until I can guarantee I don't have anything else. I've got a picture here. Okay, so I've got a picture, and you see that you have this first split here, and that corresponded with this top cell, right? And then I had the second split, and that corresponded with here, and here, and so forth. And then the next split, this was this one here, this is this one, and here, and you can see that as I'm splitting them geometrically, I'm building this tree here on the right. Okay, and now if I have a query, let's say I have a query here and I want to find the nearest neighbor, well, I first go down this tree, right? So I go down this way, I split, I go on this way of this split, it's on down here, and then I think actually there's oh, it's P7. Oh, okay. So it's like at this point it corresponds with this box here. P7 got thrown in this box. Okay.
What inherently makes this not work for higher dimensions than 10?
Okay, I'll explain that in about 1 minute, depending on how many questions I get. Yeah.
Also, how is this different than just like a multi-dimensions binary search? Because you're just like cutting your search space in half.
Well, yes, essentially this is one way of doing multi-dimensional binary search. There are other ways of doing it as well. This is one way of doing it.
How come this one doesn't have the same guarantees though as binary?
Okay, I'm about to explain that. Yeah. So, yeah.
So what do you mean when you say that median of the points?
I sort them by one of the coordinates, all the points in the subtree, and I pick the median. The points, so they're half the points on either side.
So
I guarantee that it's balanced.
So like for the rule, which coordinate do you choose? Which axis, which dimension?
Whichever one you want. Maybe you pick the one that has the most variance. Yeah, I'll come back to that point in 3 minutes. maybe 4 or 5 minutes. Okay? I'm trying to figure out my time until 4 and all the questions. Okay, so these are great questions, by the way. Okay, so now this query, I want to find the nearest neighbor. There's nothing in this cell, and identify 6. Maybe I'm down here, and I say, okay, 6 is the closest thing in this cell. I draw a circle around here. I have radius of the distance to 6. I know the nearest neighbor must fall in this circle. Maybe it goes over here a little bit. Okay? Now I need to check over in this subtree, and I say 7 is closer. So I draw a smaller radius. Okay? Now, but I need to make sure, does this cross any other subtrees? If I use the first radius, I'd go up and I'd say at this split right here, I do not need to go down into the subtree that has P9 and P10 because this circle does not cross over. But I have to go back up and check here, and I have to go down to this subtree and check for its P3 because it would have crossed over here. Okay, but because I have this smaller circle, I could have stopped here, and I don't need to go down my whole left subtree. But I have to do this pruning approach here. Okay, and so in the worst case, I may need to check a lot of the tree, right? If my query point ended up like right here, then I might need to search a lot of the tree. Okay, so I can't have the same sort of guarantees I had before because I'm now in multiple dimensions. Okay, so this works. This typically works up to about 10 dimensions if you engineer it well. What do I mean by engineer it well? Well, actually, I often reduce I reduce what I try and do a little bit, and I say I'm allowed approximate nearest neighbors. So let me draw a picture here. I'm going to say if I have a query here, and I have this is P is the nearest neighbor. So P equals the nearest neighbor of Q, and I'm going to say that dq equals the min over P and P of the distance from P to Q. All right, so I want to find a neighbor at distance. I want to find P, which would be perfect, but I'm allowed. But let's say I draw a circle of here, and that's of this distance. This is the distance here is dq. I'm willing to go up to another circle, and I'm going to say this is dq 1 plus epsilon. So if epsilon is 0.1, I'm allowing 10% error in the distance, and I'm allowed to return any point inside the red circle. Okay, and so this turns out that this, if I allow some maybe even 1% error, this allows me to do much better, because actually the pruning, it goes the other way. I can actually take the circles and shrink them by 10% or shrink them by 1%, and that causes a lot fewer of these crossover points. There's a better drawing here where there's a query point down here, and you can see these different nearest neighbors, and if I decrease the distance a little bit, I end up crossing a lot fewer of these sets. And in higher dimensions, this happens more and more. I save a lot of pruning if I can reduce my radius by 1 to 10%.
And let's say if we cannot find a neighbor within that smaller radius, do we then go back to check the larger, or do we just return no nearest neighbors?
Well, then I'm done. I first find a cell, and I take the element in the cell, and I know that that's an example of something, and I don't care about anything further away, because that's the nearest. I have an example that's only that far away. So I never need to look further again. Yeah, so I have an example, and then I can stop if I know nothing within 10% closer than that intersects any cells. Okay, yeah.
So how do you decide the radius?
I go down, if I just want one nearest neighbor, then I go down to the cell that contains, includes the query point, and each cell will have 1 point in it. That gives me my initial radius. If in my search I find this point that's closer, I reduce my radius. Yeah.
Does that have so if you take the epsilon and reduce your radius to only 9% of the point that you found in that cell, does that also give you the guarantee that the nearest neighbor will be within 10% error, for example? Yeah, it means that if there was, you actually have to reduce it by 1 over 1 minus 10%, but basically it guarantees that if I use that radius, there might be another point that's closer, but if I found that other point and I expanded it by 10%, it would include the point that I did find. Right, so this essentially works. Okay, so I want to make 1 or 2 more points, and then we're going to move on to the ethics part. Okay, so this works up to about 10 dimensions. In higher dimensions, it really only works if your data is somehow structured in some way. But then you just change the KD tree slightly, and the idea is you split dependent on data. Okay, so at every dimension, instead of choosing one of the axes, I'm going to pick some direction that somehow depends on the data. And there are kind of 2 ways of doing this. I'm going to do PCA on the data and go down to 1 dimension, and I'm going to split on this dimension, or I'm going to do 2 means clustering. So which k-means clustering we'll see next week. I'll do 2 means clustering, and I'll split based on the separator of those 2 means. And I do this at every subtree on the way down. And what this allows it to do is it allows the KD tree to adapt to the structure of the data. And there's been reports of this working really well up into hundreds of dimensions. Again, if your data was completely uniform inside of a box,
in 100 dimensions, it may not work so well, but if it's structured, then it tends to work. Okay, I wanted to say one more thing, and maybe I'll do that. There's a cute mathematical thing about high dimensions I'll do maybe at the beginning of the lecture on Monday. It's Wednesday, right? Okay. Next week, Monday. All right. Okay, good. So this was, I think I covered pretty much what I wanted to cover for the topics. I want to pivot to this question about the ethics of using the ethics of using these word embeddings. Okay? So, okay. Well, before we start, so who looked at the paper I linked and asked you all to read? Okay, can be honest. Okay, and who didn't? Okay, that's pretty good. And who took Suresh's Ethics of Data Science class last semester? Okay, so just a few of you. Okay, so, okay, good. So, all right, so just to summarize what this paper is doing, is the paper was saying, okay, you can take these data sets, you can embed them into high dimensions, but there were certain of the vectors, right, and we had discussed this a little bit, that might be between, say, the man and woman vector. And also if you do, it may be something like you have king and queen, and he and she, and they kind of have a similar alignment. And what ends up happening is that there's some vector that kind of represents the gender in this data set. Okay, so this on itself, without thinking too much more about it, you're like, okay, this is a cool thing to see, right? But then you might end up looking at other parts of the data set, and things that if you're often on the woman's side, it seems it's problematic, and in general for society, I think it's problematic. You might get these things where there's a doctor vector up here, and if you mapped this gender vector over, this will map to things close to like a vector for nurse, right? And there have been examples where for instance, people took a piece of text and they said, she is a doctor and he is a nurse, and they mapped them into Turkish, right? So there are these like so like Google Translate has something maybe similar to this at its core somehow, maybe using similar data sets, and it maps it into Turkish. And apparently in Turkish, he and she both map to a gender non-specific pronoun, like I think it's O. I don't speak Turkish, so I'm not sure. But then if you map them back, it will map to he is a doctor and she is a nurse. Right? So just by translating there and back, you kind of swap the gender because of this sort of bias that's inherent in this data set. Okay. Another potential issue is I mentioned you can do this sort of sentiment analysis, which is a very common desirable thing. But you can also do other things, like I want to say good versus evil, right? Okay, and let's say that there is a good minus evil vector, right? Okay, so I can say all words, I can score them, I can project them onto this one-dimensional space by learning good minus evil and maybe taking other words which I said correspond to good and evil and learning this best direction here. And it could, maybe this indicates that, so in this case, the woman and the nurse are more good, and the man and the doctor are more evil. Okay, so now I've classified things by good and evil, and I say men are more evil, than women, and maybe this doesn't make the men feel good, right? So there are things that, and so this is used when you're trying to kind of, people run machine learning and build classifiers on good and evil based on this data set, and things have this gender quality which automatically gets these other labels to it. Okay, so this seemed, so people noticed this and said, okay, so there was a NIF paper from a couple years ago that said, how can we possibly fix this? And they proposed a solution where they would learn this gender vector and then they'd subtract it, right? So they'd go from R300 to R299. I got rid of one dimension. I can project along this high dimensional vector. For every vector, I can project out to the gender vector, and then I can subtract that. And what I get is a 299 dimensional space that is supposedly devoid of the gender connotation. Right? I can still learn this good versus evil, but all the gender things should then hopefully not, man and women should hopefully project onto the same spot. So it's supposed to remove this connotation. Okay, so this was what this paper was about. So what do people think? Does this seem like this solves the problem? Any thoughts on it?
Or, I guess I didn't get to the end part, but like, were there results of this experiment that like the data was still useful and somehow
Yeah,
better?
so like if you look at the scores of classifiers, they still are useful classifiers, right? They still do better than not using the data, but their scores, their generalization scores may have been a little bit lower.
Okay.
Right, so you're losing some information, but you would expect that, right? Maybe according to the data set, when there's cross-validation and so forth, women do tend to be more associated with good things, and so that helped in the classification, right, based on that data set. So your score on the generalization score was higher, right?
So like I see this as like potentially very useful for like eliminating like specific biases, but there's tons of biases. So like how does this get like scaled for like trying to like get rid of other biases?
Sure. So I mean, I've got 300 dimensions, and okay. So here's one thing. There's a class of like 6 or 7 different traits that the U.S. law specifies you cannot, you can't discriminate by these traits in any sort of business in certain ways. And you could try and learn all of these traits and factor all of these out. I still have 294 dimensions, and that should be enough to be useful, hopefully. So I could potentially do that.
Yeah.
So.
Yeah, so the layout of the points depends on the data, which was extracted from statistics, like from humans, right?
Right.
So basically what we want is the computer not to learn the gender bias that is present on humans, basically is that.
Yeah, right. So the idea is that, say this comes from all of Wikipedia. That's one of the common data sets people use. There are other ones based on news sources and so forth. And say, apparently in Wikipedia there's some sort of gender bias. And this is supposed to, best effort attempt to remove this gender bias. That's the goal of the paper.
On one hand, I kind of think that we really do need to do this because I think, well, a more insidious example that I heard about is you can predict like racial identity pretty accurately by using like geolocation where somebody lives. And I think it was actually a case maybe in the wild where like they were evaluating like resumes and like that was into a classifier. And maybe it's not, I guess, immediately intuitive at first glance as you're building this thing that, oh, wait, if we include like address, like maybe on one hand like, oh, they live closer, that's good for the job. But on the other hand, the classifier could start bias against racial groups. But on the other hand, I also kind of think that also points out the problem with this, which is that some of these things seem like they're so correlated, and by getting rid of maybe gender, but it's not really straightforward all the time to just remove these things out of your data set, that they can still be computed by an algorithm to a greater or lesser degree.
Yeah. So there are a lot of great points. Let me kind of add up a bit to a few things you said. So I think it was in the males in the 1960s. I'm kind of guesstimating on that. There were these court cases where there were these loans that were being given out by banks, and they were forbidden from using race information, but they could use the zip code of where you lived, and they knew, okay, 95% of the people in the zip code are one race, and this zip code is a different, and they would use that information instead. So there are these laws about like disparate impact and so forth that tried to correct these sort of things, right? So this is an attempt to try and factor those sort of things out. Now you're right in that, okay, let's say I decided this was the gender vector that described it, but this is one vector, and it doesn't perfectly align between king and queen. That gives something slightly different, a slightly different vector. And maybe there's other side information which is still remaining in there. How do I know if I'm capturing that or not? Right? It's hard to know if this is doing a perfect job of completely removing all of the bias from it. I agree with that. Let's take some more comments. I'll come back to something later. Yeah.
I actually realized I'm kind of confused. So how do you choose which words to remove this bias from? Just from the ones that you know they should be similar? Or?
So from all of the words. From every word in the data set, I'm reducing the dimension of my space by 1. I'm removing this. Think of it, I can think of there's a hyperplane, a 299 dimensional hyperplane that runs here, and this gender vector is normal to it. I'm projecting every single word onto this hyperplane. It's still 299 dimensions, right? So I do that with all of my words, and then I can only operate in that space. Got it.
Wouldn't the issue be more that the information being used to train these vectors is biased rather than...
Great point. Okay. Yes. So there's another competing paper that I didn't link to. I didn't want to overload you. That was in Science. Came around the same time. That argued that you should not do this. And there were 2 reasons for that. One reason was it said you can build classifiers, and then you should check whether they have this inherent bias. And if they have the inherent bias, then you should be worried about your about your data set, right? And this kind of comes to the point of, does it make sense to try and build these sorts of analogies on the Wikipedia data set or another data set? Right? If there's inherent bias in the data set, should I be doing this? Right? Why do I think I should be able to understand this doctor-nurse relationship from Wikipedia? Why do I think that's a good source to learn that from? Right?
Yeah. So Professor Subramaniam did like a tech talk at the Salt Lake City Library where he said that machines are pretty good at eventually finding a bias. Even when you tend to remove it, so that's what was being said, I guess, a little while ago. So and then he also said that it's really hard to test linear classifiers and find out what bias they used, because it's more like a black box at that point. So how would you test a linear classifier?
Right. So I mean, one simple way, if you did know this gender vector, and you have the classifier is defined by normal, it turns out you need a normal and an offset. Right, and you can take these two, the normal vector and the gender vector, take their dot product. If the value is not 0, that means, which would mean they're orthogonal to each other, that means that inherently there's some bias. Right, now is that statistically significant? That means if it's significantly away from 0, probably there's some bias. But you don't necessarily know this gender vector, and it could be it's encoded in other ways. So you're right, it's not necessarily so simple. But that would be kind of, at least kind of geometrically, one way you can think of doing it. You and then maybe
the tricky thing about basing this strictly on choosing the data set that's going to be used to train on is that historically there's been a lot of bias. So most data sets that you find to train on will have biases in them. And so at least until we get better data sets, something like this could be very helpful to mitigate that.
And I guess like different states have like different thresholds for it as well. For like, especially like, there's like crime detection especially, where like there's a lot of bias in previous data sets. Yeah, just like, they think that it's just good enough to like just adjust the threshold a little bit.
Yeah, so if you couldn't hear it, you're saying in crime detection, there's known to be a lot of bias in these sorts of things. Yeah, so you're saying, I missed the second point, you said you could adjust the threshold.
Yeah, so they with this much certainty, like that certainty factor, for different states there's just different thresholds that they tend to use.
Of whether they think that this is a high crime area, we should do something special, set a policy about that.
Which according to like in the tech talk specialists, like, well, that's not the solution. You need to get rid of that initial bias. So
Yeah. Let's go here, or well, your hand was up earlier.
No, it wasn't.
Oh, okay.
Seems like kind of orthogonally to this, an interesting application could be to look at like something like a judge, right, and analyze like all of the court cases that they've done, and then analyze like these actual biases on like their hearings, and like go the other way to see what biases they have in retrospect.
Yeah, so people have done this, and there are certain biases that judges have. And the other thing that's happening is judges are now sometimes being given machine learning algorithms, and they get a court case, they throw in a bunch of data about the person on trial and what they've done, and the judge is given a probability generated somehow that they're going to commit another crime, right? And they use that in sentencing, and that data, I've heard questionable things about it, where that data comes from for various reasons. So if any of you want to talk to Suresh about it, I'm sure he'd be interested. He's looked at a lot of these things a lot recently. Okay, I haven't heard from you yet.
So I was thinking, man and woman and king and queen are they should have approximately the same distance from each other. So could we adjust the threshold which defines the gender vector? So because doctor and nurse is a little more of a stretch than a man and a woman, right?
Yeah, so it could be that there's a scale here, right? And the gender is captured on some scale, and then you could try and put you only make a prediction if you're completely sure about it. It's so far away from the separator. In high-dimensional space, these things kind of get a little bit messed up, and I'm guessing that won't work that well. That the margins tend to be fairly small, so you're probably going to lose a lot more predictive power doing that. Is my guess, that if you retrained it on the projected space, but that might work. I mean, it's worth understanding. Maybe after I do this, then after I do this projection, I look at all the pairs of words and I say, okay, now they're not all directly on top of each other, but they're pretty close, and now I have a smaller margin that I can use as a safety buffer. Maybe something like that would work. That's an interesting idea. Yeah, maybe over here.
I mean, so like I can see why in some cases you would want to do this, but saying that you should blanket do this in general seems kind of silly. If by some black magic you have a list of 15th century priests, Catholic priests specifically, you probably don't want to remove the gender bias there because only one gender was allowed to be priest in 15th century. Seems pretty accurate there. It might just destroy your entire data set if you try to remove that.
Yeah, so it could cause some other strange effects if you do this, right? It's gonna, as I mentioned, they reported that the classifiers degraded in their power, and so that's probably one of the reasons why. Yeah, so it's not. Yeah, it's a trade-off. Yeah.
It seems like kind of too with all these issues with the bias that kind of as data scientists, we do have like kind of an obligation to educate the public about this and also make sure that these algorithms aren't just offline things, since it seems like you could end up like convincing and saying like to a judge and being like, okay, you're a racist, you need to whatever, seems like maybe that's almost more feasible than trying to fix your racist algorithm. And at least it's more obvious to people a lot of times if that's happening. So it seems like that's a really big danger, is that maybe even if there's the same level of bias, the bias has more persistence power in informing an algorithm.
Yeah, so these are good points. This kind of realization and formalization of this bias that comes up in algorithms and data and machine learning is fairly new, and there's an active debate about what's the right thing to do about it. Should we try and correct for them, or should we just inform people that there is bias and maybe a policy solution is somehow better? Okay, so we're at the end of class. This was great. I thought this was really cool. I just want to leave with one, I think, important takeaway is that you should be careful where your data comes from in what you're trying to predict. If you take data from Wikipedia and try and learn something that has nothing to do with Wikipedia about that data, things might go awry. Maybe you can fix it, maybe you can't, right? So let's leave it there. All right. So this was fun. We'll see you next Monday.
Something else.